This is Chapter 8, Gases. Section 8.7 is the ideal gas law. In Section 8.5, we saw the combined gas law that expresses the relationship between the pressure and the volume and the temperature for a gas system. And in Section 8.6, we saw Avogadro's law, which expresses the relationship between volume and number of moles. So now we're in a position where we can combine both of these together and finally include the number of moles in the overall gas law. Okay, and so what we end up with is this expression where P1V1 divided by N1T1 equals P2V2 divided by N2T2. Okay, this combines all of the previous gas laws that we've talked about. And it has the advantage that we don't really need to assume that any variable is held constant. Okay? All four variables for a gas, all four properties of a gas are accounted for. So we can look at changing any combination of them. We can change one or two or three and then see how the others change as a result. Okay? What it shows us really is that the expression PV over NT is a constant for any gas. Okay, so no matter what variables you change, as long as you take the pressure, you multiply it by the volume, you divide it by the number of moles multiplied by the temperature, you're always going to get the same number. So this term, PV divided by NT, since this is a constant, we can name it. We can call it the ideal gas constant. It's also called the universal gas constant because it's true of every gas anywhere. Okay, this is denoted by the letter R. Okay, and so by putting this as R, we can actually rewrite that equation as PV over NT equals R, right? Because we can just sort of drop the subscripts. We don't need to worry about whether we're talking about under one condition or another condition. It's just anytime you have a gas system, you take the pressure, you multiply it by the volume, you divide it by the number of moles multiplied by the temperature. And as long as you do that, you're always going to get the same value R. Okay? So we can rearrange this into the more commonly seen form, which is this, the ideal gas law, PV equals nRT. The pressure times the volume equals the number of moles times this universal constant times the Kelvin temperature. Okay? So this is a very important law for this chapter, for the chapter on gases, so this is something you should definitely remember. In fact, all of the previous questions that we looked at in this chapter can really be answered using the ideal gas law. So any question on Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, the combined gas law, they can all be answered by using this one law appropriately. So what is R? The ideal gas constant, the universal gas constant, right? But what is the actual number for R? Well, to find out R experimentally, it's very straightforward. You take a gas in a certain volume, you measure the temperature that the gas is at, you measure how many gas particles you have, and you measure the pressure that the gas exerts. You take all of these values that you measure experimentally, and you put them into this expression, and you calculate R. Okay? For our purposes, we're not really going to run the experiment here, but we already know some facts about gases that will help us. Okay? In the previous section, the previous video, we saw that the molar volume of a gas at STP is 22.4 liters. Okay? So 1 mole of any gas will occupy a volume of 22.4 liters at standard temperature and pressure, which means 273 K and 1 atmosphere. So this is all of the variables that we need. It's N, it's V, it's T, and it's P. Okay? So once we have all of them, we can just put them all into the expression PV over NT. Okay? 1 atmosphere of pressure, 22.4 liters per 1 mole at 273 K. And so we multiply all these together and we get 0.0821 liter atmospheres per mole per Kelvin. Okay? It's a little bit of a strange unit. It's an amalgamation of all the different units, but it's very important to pay attention to this unit. Okay? We'll see why in a second. Now, real gases do show some deviation from this ideal behavior. They don't exactly follow the ideal gas law. Nevertheless, it is a really, really good approximation for most real gases under normal conditions. Okay, so it's very rare that you'll need to use anything more sophisticated than the ideal gas law to model the behavior of a gas. Okay, it works in a wide range of situations. So if we measure the pressure, the volume, the temperature, and the number of moles for any gas system anywhere in the universe, and we measure it in units of atmospheres, liters, Kelvin, and moles, then we're always going to get that same value for R, 0.0821. However, if we measure one of those properties in a different unit, then the numerical value of R will change. Okay, so for instance, if we take the same idea, right, 1 mole at STP has a volume of 22.4 liters, but now we express the standard pressure in millimeters of mercury instead of atmospheres. So 1 atmosphere actually equals 760 millimeters of mercury. So if we put that value into the expression for R, then we get a different number, 62.4, and the unit is now liters times millimeters of mercury per mole per Kelvin. Okay, so the value changes, but only because the unit changes. So it's still a constant, it still expresses the same fundamental underlying property of gases, it's just expressed in a different unit. Okay, so when you use the ideal gas constant in a calculation, in other words, anytime you're using the ideal gas law, you have to make sure that you choose a value of R that has the right units. Okay, if you're given all of your pressures in millimeters of mercury, then you can't really use the R that has atmospheres. Okay, now I recommend that you remember that first value of R that we saw, 0.0821 liter atmospheres per mole per Kelvin. Okay, again, in the past, that's what would have been given to you on the exam, but it's the most common value of R used in chemistry because those are the most common units. So if that's the R that you remember, then all you have to do is remember to convert all of your volume units to liter and all of your pressure units to atmospheres. Okay, the number of moles is really always going to be in moles, so if they happen to give you particles or something like that, then you just use Avogadro's number to get the number of moles. And temperatures, again, should always be in Kelvin. You don't really have a choice there. But for volume, as long as you use liters and atmospheres for pressure, then you can use this value of R. Let's do an example. Dinitrogen oxide, N2O, which is also known as laughing gas, is used as a general anesthetic in dentistry. What is the pressure in atmospheres of 0.350 moles of dinitrogen oxide at 22 degrees Celsius in a 5-liter container? Okay. Now, this is a question that you need to use the ideal gas law for. Okay? None of the other gas law equations really fit the information that we're given. Okay? In other words, we're not looking at a gas that's undergone some change. We're not looking at comparing one gas system to another that has certain properties in common. We're just talking about a gas system, and we're given 3 different properties of it. We're given, in this case, N, the number of moles, we're given T, the temperature, and we're given V, the volume. Okay? So this tells us that we're going to need to use the ideal gas law. So again, this is our first step. Analyze what we're given. We have the volume, the number of moles, and the temperature, and we're asked to find the pressure in atmospheres. Okay, so we want P. So at this point, we should know that we're dealing with the ideal gas law, and so we'll also need to know R, the gas constant, 0.0821 liter atmospheres per mole per Kelvin. The next step is going to be to rearrange the ideal gas law to isolate the variable that we're looking for. In this case, again, we're looking for the pressure, so we're going to want to get P all on its own. So to do that, it's very simple. You just divide both sides by V, okay, and that cancels out. And so you end up with P equals nRT divided by V. Okay. Now, be careful. This is relatively simple algebra. You should practice this and make sure you're able to do this. But it's very easy to just get mixed up and sort of divide by the wrong thing or put it on the wrong side. So just be careful with what you're doing with the algebra for these kinds of questions. Once we have that formula, we just put in the values that they gave us, right? So P equals nRT over V. So this is N, 0.350 moles. This is R, 0.0821. And this is T, 295 K. Okay. I did skip something, which was to remember that this temperature in Celsius always has to be in Kelvin. So 22 degrees Celsius plus 273 is going to be equal to 295 K. Okay, very important to put all of your temperatures into Kelvin. And then the last thing is on the bottom here, we have the volume, 5 liters. So you multiply all these together, divide by the volume, and you end up with 1.70. And the unit here is atmospheres because Kelvin cancels Kelvin, moles cancels moles, liters cancels liters, and we're left with the pressure unit from R, which is atmospheres. So here we could have used the other one that we calculated earlier with millimeters of mercury, and then we would get an answer that's in millimeters of mercury. Okay? But this question asks for it in atmospheres, so we want to use the one in atmospheres. Okay? So your final answer is 1.70 atmospheres. Now that we finally know the ideal gas law, we can really look at how to figure out the number of moles of a gas from the observable properties, from the pressure and the temperature and the volume. Which is going to be very useful when we deal with chemical reactions involving gases. So gases are involved as reactants and products in a large number of chemical reactions, and we know that the chemical equation for these types of reactions is always going to relate mole quantities of the substances. Okay? So the chemical equation always tells you mole to mole ratios. So in dealing with solids, we wanted to be able to relate the mass to the number of moles because it was easy to measure the mass of a solid on a scale. So to convert mass to number of moles for use in the equation, we used the molar mass. Okay? And that was a lot of what we did in previous chapters. Now that we're dealing with gases, if we have a chemical equation with gases, we want to be able to relate the gas properties, pressure, volume, and temperature to the number of moles. And so now we're going to use the ideal gas law. Let's look at how this works in an example. A nitrogen gas reacts with hydrogen gas to produce ammonia gas, NH3. Again, we've seen this equation many, many times before. How many liters of ammonia, that's the product, NH3, can be produced at 0.93 atmospheres and 24 degrees Celsius from a 16-gram sample of nitrogen gas and an excess of hydrogen gas? Okay? So luckily they told us that we have excess hydrogen gas, so we don't need to worry about calculating limiting reactants or anything like that. But we know we're given the mass of nitrogen and we're asked to find the volume of ammonia. So let's analyze the problem. We are given the mass of nitrogen, that's the mass of a reactant, and we're asked to find the volume of ammonia, which is the volume of a product. Okay? So we know that in order to relate one substance to another in the chemical equation, we're going to need a mole-to-mole factor, or mole-to-mole ratio. That means that in order to figure out moles of ammonia, we'll need to get moles of nitrogen. So we're not given moles of nitrogen, we're given mass of nitrogen, which means we're going to need a molar mass. Okay? And then at the end, on the other side, we are going to need to get the volume of ammonia from the number of moles. So in order to do that, we'll need the ideal gas law. Okay, which is PV equals nRT. So luckily, we're also given the pressure and the temperature in the question, as well as the balanced chemical equation. So with all this, we should be able to attack the problem. So write a plan to convert the given quantities to the needed volume. The initial quantity you're given is grams of nitrogen. And again, when we're trying to convert one substance to another, we have to go through the mole-to-mole factors. So the first thing you should do is try and figure out how to get from grams of nitrogen to moles of nitrogen. Clearly, we're going to use the molar mass of nitrogen to do that. Then we can finally relate the amount of a reactant to the amount of product using a mole-to-mole factor from the chemical equation. Okay? Moles of nitrogen will be transformed into moles of ammonia. And then at the end, we have moles of ammonia, but we want to get the volume of ammonia in liters. And so since this is a gas, we can convert moles to liters using the ideal gas law. Okay? Now, remember, if this were at standard temperature and pressure, we could just use the molar volume of 22.4 liters. Okay? But it's not standard temperature and pressure. It's 0.93 atmospheres and 24 degrees Celsius. Okay? So keep in mind, this is not an STP problem, so instead of using the molar volume, you have to use the ideal gas law. So then we can write down our relationships and our conversion factors. Okay? For the molar mass of nitrogen, you have 1 mole per 28.02 grams. And the mole-to-mole ratio is that 1 mole of nitrogen will produce 2 moles of ammonia, or 2 moles of ammonia requires 1 mole of nitrogen. And then we can just put these in. We start from the mass, grams of nitrogen, convert that to moles using the molar mass so that we cancel grams of nitrogen. Right? That means the grams goes on the bottom here, and that leaves us moles on top. And then we have a mole-to-mole factor, where we cancel moles of nitrogen, and we're left with moles of ammonia. Okay. Now at this point, in previous problems, in previous chapters, we would have one more conversion factor where we just go from moles to mass or something like that. But in this case, we need to go from moles to the volume of a gas. And so you can think of it as a conversion factor and try and fit the ideal gas law as another conversion factor on the end, but it's a little confusing to think about it that way. So it's better to just calculate the moles of ammonia and then put that into the gas law, PV equals nRT. Okay? This 1.14 moles is N in the equation. Okay? So once we have it, then we can just solve the gas law. We're solving for V this time. So from PV equals nRT, we're going to divide both sides by P now. Okay? And that'll cancel P on the left side, and you'll end up with nRT divided by P. Okay? So now we were given the pressure, we were given the temperature. We just have to remember to convert this to Kelvin. So 24 degrees Celsius plus 273 is going to be 297 K. Okay. So that'll be the temperature. We know R, we can just look it up or have it written down, it's 0.0821. And then the last thing that we needed was N, the number of moles, which we got from the mole-to-mole factor. Okay. So again, it's important to recognize what it's asking you for. When you're asked for the volume of ammonia at a certain temperature and pressure, you should know that you need to find the number of moles of ammonia. And that means not just taking the mass and putting it in, because it looks like it's the only other number you can think of, but actually trying to figure out how do you get moles of ammonia from the amount of nitrogen, right? And how do you get moles of ammonia from moles of nitrogen? And so then to get moles of nitrogen, you need to get it from the mass of nitrogen. Okay, so sometimes it helps to start at the end and then sort of work your way backwards to see what it is that you need. Okay. So, but once you're at this point, you just put everything in. 1.14 moles, 0.0821 is R, 297 K, and 0.93 atmospheres, and you end up with the total volume of 29.9 liters of ammonia.